Welcome to the Electrical Grid Testing and Commissioning Training module, focusing on power transformers. This module, part of our 2026 training program, is designed to equip you with the essential knowledge and skills needed to effectively test and commission power transformers within electrical grids. Let's get started on this critical aspect of electrical infrastructure. On this slide, we focus on the reference framework for testing and commissioning electrical grids. This framework serves as the backbone for our commissioning manuals and test scripts, ensuring consistency and reliability throughout the process. We rely on several key standards organizations, including the IEC, which stands for the International Electrotechnical Commission, and the IEEE, or Institute of Electrical and Electronics Engineers. Others include ASTM, NEMA, ANSI, SIGER, ICA, and KEMA, each contributing specific guidelines or certifications essential for our work. A crucial governance rule here is to always apply the most stringent approved requirement whenever there is a conflict between project specifications, manufacturer instructions, and established standards. It's also important to document which reference was used on the test sheet. This practice allows anyone reviewing the results in the future to understand the basis for acceptance and ensures full traceability in our commissioning process. Here we have the schematic for the insulation resistance testing of power transformer windings. This diagram is specifically for a 5 kV DC test, covering the high voltage, low voltage, and tertiary windings. Proper insulation resistance testing is crucial during the commissioning of transformers to ensure electrical safety and reliable operation. This slide is part of the commissioning manual, providing a clear reference for technicians performing these tests on the electrical grid. Here we have the detailed procedure for the power transformer winding insulation resistance test, which is crucial before proceeding with further tests or energizing the transformer. The primary goal is to verify the insulation integrity between transformer windings and ground to ensure safety and reliability. We base this test on approved references like PR NG 6460-002, along with the transformer's drawings and nameplate data. The equipment used includes a calibrated 5 kV DC insulation resistance tester, commonly known as a megger, along with necessary safety tools like discharge rods, PP, and barricades to secure the test area. The process is clearly defined in a step-by-step script. We start by confirming transformer details and verifying the testing boundaries against the drawings. Next, we review all safety and operational permits, followed by preparations such as cleaning the bushings and terminals to eliminate any contaminants. We proceed by connecting the insulation resistance tester to each approved boundary: high voltage to ground, low voltage to ground, tertiary to ground, and winding to winding if required. We then apply the specified DC test voltage for the duration defined, carefully watching for any instability or abnormal discharge. It's essential to accurately record all relevant data, including resistance values, voltage, test duration, temperature, humidity, and instrument details. After each measurement, we safely discharge the windings to avoid stored voltage hazards before moving on. Finally, we restore all links, grounds, and terminal covers to their approved as left condition. Acceptance criteria dictate that insulation resistance must meet manufacturer and project limits with stable readings and no signs of flashover or damage. The results package includes the IR test sheet, photos, environmental conditions, calibration certificates, and witness signatures. A key hold point is that the witness verifies safe discharge, acceptable insulation resistance values, and proper restoration before allowing the test sequence to continue. This thorough protocol helps maintain transformer safety and operational integrity during commissioning. Here we have a schematic related to the power transformer's core and frame insulation. This diagram is crucial because it outlines the testing points for core-to-earth, frame-to-earth, and core-to-frame insulation using 1 kV DC. Understanding this schematic is essential for ensuring the insulation integrity during commissioning. This step helps verify that the transformer will operate safely within the electrical grid without insulation failures. The information is detailed in Commissioning Manual number 4-2, providing us with the standardized procedure for these tests. This slide outlines the power transformer core and frame insulation test at 1 kV DC, which is crucial for ensuring the transformer's core, frame, and earth links are properly isolated or bonded as per design. We rely on several references, including the approved transformer manual and earthing drawings, to guide this process. We use calibrated 1 kV DC insulation resistance testers with guard terminals, discharge leads, and the necessary PPE for safety. The testing script is detailed and methodical. First, we identify all relevant links and earth references before disconnecting anything. Then, we confirm transformer isolation and safe access under an approved permit. Only the approved core or frame link is removed, with its original position recorded. We connect for core-to-earth, frame-to-earth, and core-to-frame tests following the schematic. Applying 1 kV DC for the required duration, we observe insulation values until they stabilize. After each measurement, it's critical to discharge to prevent any part from unintentionally floating. Once testing is complete, we reinstall the link securely, verifying continuity to the correct earth point. All values, link restorations, photos, and witness confirmations are recorded. The acceptance criteria emphasize that no link should remain removed, loose, or misplaced after testing. Finally, the result package includes insulation tables, photos before and after link removal, checklists, instrument calibration, and witness sign-off. A hold point requires witness confirmation of both link restoration and acceptable insulation values before proceeding further. This ensures safety and compliance at every step. Here we have the schematic for measuring the winding resistance of a power transformer. This diagram is essential because it shows how to perform low-resistance measurements on the windings, specifically by phase and tap position. Understanding this process is crucial during the testing and commissioning of the electrical grid to ensure the transformer operates reliably. The reference provided, Commissioning Manual number 4-3, offers detailed guidance to follow these procedures accurately. Let's walk through the power transformer winding resistance test, which is essential for ensuring the transformer's reliability and safety. The main goal here is to verify winding continuity, joint integrity, phase balance, and consistent tap changer contact. We base our work on key references like the transformer nameplate, winding diagram, tap schedule, factory report, and specific procedures alongside the resistance test form. For this test, we use calibrated instruments such as a low-resistance ohm meter or micro-ohm meter with Kelvin leads, a DC current source, discharge controls, and a data logger. The testing process follows a clear sequence. First, we confirm terminal names, tap position, winding configuration, neutral links, and check for the required reference temperature. Next, we verify the transformer is fully de-energized, isolated, discharged, and safe for testing. Then, Kelvin leads are connected firmly to clean metal contact points on the selected winding terminals. We inject an approved DC test current and wait for readings to stabilize before recording. All phases and tap positions specified in the test plan are measured. After that, we compare phase balance and tap progression against factory baseline values and project acceptance limits. Remember to discharge winding energy before changing connections or tap positions. Throughout, detailed records are kept, including current, resistance, temperature, tap position, instrument serial number, and the as-left condition. Acceptance criteria require stable, phase-balanced values consistent with the transformer's design and tap position. Any open circuit, unstable readings, or abnormal deviations are not acceptable. Finally, the result package includes a resistance report, tap position table, terminal photos, a comparison summary, instrument certificates, and witness sign-off. The hold point ensures a witness confirms the final tap position and the removal of the test current before the transformer is released for operation. This meticulous approach guarantees the transformer is safe and ready for service. Here we have the schematic for measuring power transformer excitation current during no-load conditions, using controlled voltage injection. This method is crucial for accurate assessment of the transformer's excitation characteristics without applying load. By injecting a controlled voltage, we can precisely evaluate the excitation current, which helps identify any anomalies early in the commissioning process. Understanding this schematic is fundamental to ensuring reliable transformer operation in the electrical grid. This slide outlines the power transformer excitation current test, which is essential for verifying the magnetic circuit condition and ensuring phase balance before energizing the transformer. The test helps detect any abnormal core or winding behavior early on. We start by reviewing critical reference data, such as the transformer vector group, winding diagram, and factory no-load data, which guide the test setup. For equipment, we rely on a calibrated variable voltage source, voltmeter, ammeter, wattmeter, or power analyzer, along with proper personal protective equipment. The step-by-step test begins with confirming the test winding, positions, and voltage relationships. Next, it's crucial to ensure that non-tested windings are correctly isolated or connected as per the approved schematic. We then connect the voltage and current instruments with the correct phase reference and polarity to maintain measurement accuracy. Voltage is raised gradually to the approved test level while continuously monitoring current, sound, and any signs of abnormal heating. Measurements of excitation current and no-load losses are taken for each phase, followed by a careful comparison of phase symmetry against manufacturer data or baseline readings. After completing measurements, voltage is reduced to zero, discharged, and safety conditions verified before making any connection changes. All readings, tap positions, and witness observations are recorded meticulously. Acceptance criteria highlight that excitation current should be balanced and consistent with factory data. Any excessive current, instability, unusual noise, or heating must be investigated promptly. Finally, the result package includes all test records, phase comparisons, instrument calibrations, setup photos, and witness sign-off to document compliance. Before proceeding to the next test, a hold point requires confirmation from the witness that voltage has been safely removed and the transformer condition is secure. This thorough process ensures transformer reliability and safety in the electrical grid. Here we have the schematic for the power transformer's short-circuit impedance, which is essential for proper testing and commissioning of the electrical grid. This diagram serves as a key reference for short-circuit percentage impedance testing by using measured voltage, current, and power values. Understanding this schematic helps ensure accurate assessment and reliable operation of the transformer during grid commissioning. This slide outlines the power transformer short-circuit impedance test, a critical step in testing and commissioning electrical grids. The main goal here is to validate the transformer's impedance and winding condition, which ensures accurate data for fault level calculations, load flow analysis, and protection settings. We start by referencing important documents like the nameplate %Z, factory test report, winding connection diagram, tap schedule, and an approved impedance test form. The instruments involved include a calibrated low-voltage three-phase source, ammeter, voltmeter, wattmeter or power analyzer, shorting leads, and personal protective equipment. The step-by-step testing script guides us through the process. First, confirming the energized and shorted winding, tap position, and test limits. Then, securely installing current-rated shorting links on the non-energized winding. Next, connecting measurement instruments per the schematic and verifying phase sequence. We then gradually increase the injection voltage until the approved test current or condition is met. Key measurements, voltage, current, watts, and tap position, are recorded to calculate the percentage impedance. This process is repeated for required tap positions or winding combinations. After testing, voltage must be reduced to zero before authorized removal of temporary shorts. Results are compared with nameplate and factory data, documenting any deviations or retesting needs. The acceptance criteria emphasize that calculated impedance must align with manufacturer data within approved tolerances, with no unbalanced current or abnormal losses allowed. Finally, the evidence package includes impedance calculations, photos of shorting links, instrument calibrations, phase readings, and a witness sign-off. A crucial hold point requires a witness to verify the removal of all temporary shorting links before proceeding with further testing. Here we have a schematic for the zero-sequence impedance of a power transformer, which is crucial for understanding how current flows during ground faults. This diagram shows the testing setup using linked phase terminals and controlled injection methods. By accurately measuring the zero-sequence impedance, we can ensure the transformer performs reliably within the electrical grid. This process is an essential part of the commissioning and testing phase, as outlined in Commissioning Manual number 4 to 6. This slide outlines the zero-sequence impedance test for power transformers, which is crucial for earth fault studies and protection settings. The test confirms the zero-sequence impedance to ensure correct neutral and grounding coordination. We start by confirming the test winding, neutral condition, grounding arrangement, and tap positions according to the study. Next, we verify that non-tested windings are properly shorted open, or grounded per the approved schematic. Then, with the transformer isolated and discharged, phase links and test jumpers are installed. A controlled voltage is applied to the linked phase group, while voltage, current, and power measurements are recorded. From these, zero-sequence impedance and its resistance and reactance components are calculated. These values must be compared against protection study assumptions and manufacturer data to ensure accuracy. After testing, the injection voltage is removed, equipment is discharged, and neutral and ground links are restored to their original state. All readings, calculations, photos of connections, tap positions, and witness confirmations are documented thoroughly. For acceptance, zero-sequence impedance must fall within the approved tolerance and align with protection study requirements. Any discrepancies, such as incorrect neutral state or inconsistent values, require correction and retesting. The result package includes the calculation sheet, photos, tap records, instrument calibration, and witness sign-off. Finally, the test holds at a critical point where the witness must confirm the neutral and earthing configuration is restored before the transformer is approved for energization. This step ensures safety and reliability in the electrical grid commissioning process. Here we have the schematic for the power transformer turns ratio, which is essential for testing and commissioning within the electrical grid. This diagram serves as a reference to verify the ratio across different windings and tap positions, ensuring that the transformer performs correctly under various conditions. Accurate ratio verification is critical to maintain system reliability and prevent potential faults. This information is drawn from Commissioning Manual number 4 to 7, guiding us through best practices during the commissioning process. Here we have the power transformer turns ratio test script, which is crucial for ensuring correct transformation and protection assumptions. The purpose is to verify the transformer's ratio, phase relationship, and tap changer progression. To do this, we rely on references such as the nameplate ratio, vector group, tap schedule, factory report, winding diagram, and an approved TTR test sheet. The required equipment includes a calibrated transformer turns ratio test set with phase angle measurement capability, test leads, and the option to export electronic reports. The testing involves a clear step-by-step process. First, we confirm all transformer details: the tag, winding names, vector group, rated voltages, tap range, and current tap position. Then we isolate and discharge the transformer and remove any external burdens that might influence the measurement. Next, the TTR leads are connected to selected winding terminals according to the schematic and phase reference. Once connected, we run the ratio and phase angle measurements for each phase and tap position. Importantly, tap changers should only be moved using an approved method, and the tap indication must be verified before every measurement. We then compare measured ratios, deviations, and phase displacements with the nameplate and factory values. All relevant data, tap position, ratio, deviation, phase angle, temperature, and instrument serial number, must be recorded carefully. After completing the tests, the tap changer is returned to the required as-left position, and all terminal covers and links are restored. Acceptance criteria require that the ratio and phase displacement match the nameplate, vector group, and approved tolerance across all taps. For documentation, we compile a detailed TTR report, a tap table, photos of the nameplate and connections, instrument calibration certificates, and obtain witness sign-off. Finally, the hold point calls for a witness to confirm that the final tap position is correct, the ratio values are accepted, and that no temporary connections remain. This thorough procedure ensures the transformer operates safely and reliably within its design specifications. Here we have the schematic for the power transformer magnetic balance test, which is critical for ensuring the transformer's proper operation. This test verifies the induced voltage patterns and confirms that the magnetic circuits are balanced as expected. By carefully following this schematic, technicians can detect any anomalies early during commissioning, which helps prevent future issues in the electrical grid. Remember, this is a key reference from the Commissioning Manual number 4 to 8 and an essential step in the testing and commissioning process. Now we'll go over the power transformer magnetic balance test script, which is crucial for ensuring the transformer's magnetic path consistency. This test helps us identify any possible winding displacement, incorrect connections, or core abnormalities. To perform this test, we rely on reference data like winding configuration, vector group, tap position, and historical magnetic balance records, along with approved test sheets. The instruments required include a calibrated low-voltage AC source, a voltmeter or multimeter, phase labels, grounding leads, and personal protective equipment. The step-by-step process starts with confirming the transformer's winding connections, phase designations, tap positions, and the selected injection winding. We then verify that the transformer is properly isolated, discharged, and disconnected from any external circuits. Next, we inject an approved low AC voltage into one phase winding and measure the induced voltages on the other phases, repeating this process for each phase according to the schematic. All applied and induced voltages are carefully recorded. We then compare these voltage patterns against the expected magnetic balance behavior based on the transformer's construction. If we detect any abnormal induced voltage patterns, open connections, or inconsistent core responses, these issues must be investigated thoroughly. Finally, once testing is complete, we remove the test leads, restore all terminal links, and document the as-left condition. For acceptance, the voltage pattern must align with the winding and core arrangement and match the reference data. Any abnormal asymmetry requires further investigation and retesting. The result package should include the magnetic balance table, connection photos, instrument calibration certificates, logs of any abnormalities, and a witness sign-off. A hold point ensures that a witness confirms no test voltage remains and all windings are correctly restored before proceeding. Here we have the power transformer vector group schematic, which is crucial for understanding the transformer's phase relationships and connections. This schematic serves as a key reference during testing and commissioning to verify the vector group and phase displacement, ensuring the transformer operates correctly within the electrical grid. Proper verification at this stage helps prevent issues in system synchronization and performance. This information is detailed further in Commissioning Manual number 4-9. On this slide, we focus on the power transformer vector group test, a crucial step in testing and commissioning the electrical grid. This test confirms the vector group, phase displacement, and terminal identification before paralleling transformers or releasing protections. Starting with the references, we rely on the nameplate vector group, single-line diagram, phase sequence drawing, protection scheme, and approved test form. The instruments needed include a transformer ratio and vector group test set, a phase angle meter or approved injection set, along with calibrated leads and phase labels. The testing procedure involves 8 key steps. First, we confirm the specified vector group, phase rotation, terminal markings, and system reference phase sequence. Then, we isolate and discharge the transformer, ensuring the test won't backfeed external buses or circuits. Next, the test set is connected according to the terminal schematic. The fourth step involves verifying phase displacement and clock number for required phases and windings. Then, we check terminal identification against markings, drawings, and ratio results. All measured data, including vector group, phase angles, and terminal references, are recorded, noting any corrections. The results are then compared with the nameplate and design requirements, which is especially important for parallel operation. Finally, temporary wiring is removed, and the terminal box, tap position, and grounding status are restored. Acceptance criteria are strict. The measured vector group and phase displacement must match the nameplate and design. Any wrong clock number or reversed phase is unacceptable until corrected and retested. The evidence package includes a vector group report, phase angle record, terminal photos, correction log, and witness sign-off. The hold point requires witness confirmation of the accepted vector group before synchronization, paralleling, or energization. This thorough process ensures safe and reliable transformer operation within the grid. Here we have the schematic for the power transformer tan delta test, which is crucial for assessing insulation quality. The tan delta, or power factor test, helps us identify any deterioration in the transformer's insulation by measuring the dielectric losses. This schematic specifically shows the test setup using guarded test modes to ensure accuracy by minimizing leakage currents. Understanding this diagram is essential for proper testing and commissioning of transformers in the electrical grid. Accurate tan delta measurements help prevent breakdowns and extend transformer life. On this slide, we cover the comprehensive power transformer tan delta test script, which is essential for assessing transformer insulation condition, moisture presence, contamination, and the health of bushings and windings. The test relies on references like the Transformer Insulation Test Plan, manufacturer baselines, and approved tan delta forms to ensure accuracy and consistency. We use calibrated power factor and tan delta test sets along with necessary leads and safety grounds. The step-by-step process starts with confirming test modes and winding configurations, cleaning bushings, verifying isolation and discharge, and shorting windings as needed. We then apply the test voltage, monitor measurements like current, watts, and loss factor, and record capacitance and temperature corrections for each point. Between tests, we discharge and ground the transformer to maintain safety. It's crucial to review any abnormal high losses or shifts against baselines. For acceptance, power factor and capacitance must stay within approved limits, with no flashover or unstable readings accepted. Finally, the results package includes detailed reports, photos, and witness sign-offs, with a hold point ensuring discharge confirmation before final release. This systematic approach guarantees reliable testing and safe commissioning of power transformers. Here we have a schematic specifically focused on the oil dielectric breakdown in power transformers. This is a crucial aspect when it comes to testing and commissioning electrical grids. The insulating oil sampling and dielectric breakdown voltage test are essential procedures to ensure the transformer's insulation integrity and overall reliability. These tests help us detect any potential weaknesses or contaminants in the oil that could lead to failures. By carefully following the steps outlined in the commissioning manual, we can confirm that the transformer meets all safety and performance standards before it goes into operation. This slide outlines the comprehensive script for performing a power transformer oil dielectric breakdown test, which is critical for verifying the insulating oil's dielectric strength and identifying any moisture, contamination, or handling defects. We begin by confirming the oil sampling point, transformer tag, oil temperature, cleanliness of the sample bottle, and the test method to be used. Then we take the oil sample carefully, using a clean approved technique to prevent moisture, air bubbles, and contamination. Next, the test vessel and electrodes are cleaned, and the electrode gap is set accurately. The vessel is then filled to the prescribed level. Any bubbles are allowed to settle, and the vessel is installed in the test set. We proceed to run a sequence of breakdown tests, recording each breakdown voltage meticulously. After testing, we calculate the average breakdown voltage and compare it against the approved dielectric strength criteria to determine acceptance. It is also important to document the oil condition, sampling location, ambient conditions, instrument serial number, and any retests performed. Finally, samples are disposed of or retained according to procedure, and any abnormal oil quality issues are addressed. The acceptance criteria specify that the average breakdown voltage must meet the approved threshold without signs of moisture, sediment, or unacceptable variation. The result package should include the oil breakdown voltage report, sample chain of custody, sampling photos, instrument calibration records, and witness sign-off. At the hold point, a witness must confirm acceptable oil test results or approve corrective actions before proceeding with energization readiness. This detailed process ensures transformer reliability and safety through thorough testing and verification. Here we have the schematic for the power transformer temperature sensor calibration. This diagram is crucial because it shows the reference points for calibrating the oil temperature, winding temperature, as well as the alarm and trip contacts. Accurate calibration ensures reliable operation and safety during the testing and commissioning of the electrical grid. This information is detailed in Commissioning Manual number 4-12, which guides us through the necessary steps for proper sensor setup and verification. Here we have the calibration script for the power transformer temperature sensors, focusing on both oil and winding temperature measurements. The key objective here is to verify temperature indication accuracy, as well as the proper functioning of alarm stages, trip stages, and remote signal mapping. We start by confirming sensor tags, indicator ranges, and set points against the schedule, then isolate control circuits and notify the control room before operating any alarm or trip contacts. Next, the sensor or simulator is placed in a controlled temperature source and compared to a reference thermometer to ensure accuracy. We then verify indications across various points including local gauges, marshalling boxes, protection panels, and remote interfaces if present. We simulate temperature increases through alarm and trip thresholds to check contact operation and carefully record all operate and reset points, indication errors, and any adjustments made. Finally, wiring, set points, and operational status are restored, ensuring that no unintended alarms or trips remain active. Acceptance criteria require all indication errors and contact operate/reset values to stay within approved tolerances and be correctly mapped. The result package includes calibration certificates, set point tables, screenshots, alarm logs, and a witness sign-off, which serves as the hold point confirming everything is properly restored with no forced signals lingering. Here we have the schematic for testing the cooling fan of a power transformer. This diagram is essential for understanding how to perform insulation checks, starting current measurements, and functional operation tests on the cooling fan. These tests ensure that the cooling system operates reliably and safely, which is critical for maintaining the transformer's performance during operation. This schematic is referenced in Commissioning Manual number 4-13, serving as a guide for technicians during the testing and commissioning phase of the electrical grid. On this slide, we focus on the power transformer cooling fan test script, which is essential for ensuring the reliability and safety of the transformer's cooling system. The main goal is to verify several critical aspects: the fan motor insulation, correct rotation, start and stop logic, protection settings, and load current. To carry out these tests properly, we reference key documents like the cooling control panel drawing, fan schedule, motor data, and the approved fan test form. The testing requires specific instruments including an insulation resistance tester, clamp ammeter or multimeter, phase rotation meter, and a tachometer or a visual check for rotation, along with appropriate personal protective equipment. The test procedure follows a detailed step-by-step script. First, we confirm all fan tag numbers, supply circuits, control terminals, and settings. Next, we ensure the fan circuits are isolated before performing insulation resistance tests phase to ground and phase to phase. Then, we energize the fans in approved test modes to check rotation, airflow, vibration, and noise levels. We also measure starting and running currents for each fan motor phase and verify the control logic, including manual, automatic, and temperature-driven operations, while monitoring status indications. All observations such as current, rotation, alarms, and overload settings are recorded carefully. Finally, all fans are restored to their proper service mode, and any temporary overrides are cleared. The acceptance criteria require fan insulation, rotation, current, and control operation to meet approved standards without abnormal vibration, overload trips, or incorrect status indications. The result package includes comprehensive evidence: fan test sheets, current readings, rotation proof, insulation test results, control screenshots, and witness sign-off. The hold point ensures a witness confirms that all fans are returned to correct automatic or service status before the handback. This process guarantees the cooling fans operate safely and effectively within the electrical grid system. Here we have a schematic for the supervision functional check of a power transformer. This diagram is essential for testing and commissioning activities in the electrical grid. It provides a clear reference for verifying the proper operation of supervision equipment, including alarms, trips, and indication checks. By following this schematic, we can ensure that the transformer's protection and monitoring systems are functioning correctly before they go live. This step is crucial for maintaining grid reliability and safety. On this slide, we focus on the functional check script for power transformer supervision during testing and commissioning of the electrical grid. The key task here is verifying the alarm, trip, and indication functions from the transformer accessories all the way to the protection panels and monitoring systems. To do this, we reference critical documents like the accessory schedule, marshalling diagram, protection logic, alarm list, trip matrix, and the approved functional test sheet. For the equipment, we use tools such as a multimeter, contact simulator, secondary injection kit, and a laptop or monitoring interface to access event logs. The testing process follows a step-by-step script starting with listing every supervision device, like the Buchholz relay, pressure relief, and temperature alarms. Next, we confirm the type of each contact and verify where the signals are sent. Before testing, we place protection and control systems in an approved test condition, allowing trip blocking only if authorized. Then, we operate or simulate each contact using manufacturer-approved methods. During this, we verify local enunciation, relay inputs, trip outputs, remote indications, and timestamps to ensure proper response. All operate and reset statuses, tag names, alarm texts, relay inputs, trip paths, and any corrections must be recorded accurately. After the tests, it's essential to remove all test links, simulation jumpers, and blocking devices. Finally, we confirm that the system returns to a normal state, with no standing alarms before handback. Acceptance criteria require that each supervision device triggers the correct alarm, trip, or indication at the designated destination, with precise tag text and no unintended outputs. The results are compiled into a comprehensive evidence package containing functional matrices, alarm and trip logs, screenshots, relay event records, device photos, and witness sign-off. This is also a hold point where the witness verifies that all trip blocks and simulations are removed, and that the final alarm list is either clear or accepted, ensuring the system's integrity before proceeding. Here we have the schematic for the power transformer's OLTC, or on-load tap changer, motor drive unit checks. This diagram is crucial for understanding how to properly perform contact range and current consumption tests during commissioning. These checks ensure the tap changer operates smoothly and reliably under load, which is essential for maintaining grid stability. The schematic provides a clear reference to follow, helping technicians verify that the motor drive unit functions within specified parameters. This step is part of the thorough testing outlined in Commissioning Manual number 4 to 15, reinforcing our commitment to safety and performance in electrical grid commissioning. This slide covers the comprehensive check test script for the power transformer OLTC MDU. The key focus is on verifying the operation of the OLTC motor drive, tap indication, limit switches, current consumption, and identifying any abnormal phase loss behavior. We use references such as the OLTC MDU manual, tap schedule, control schematic, limit switch diagram, alarm list, and the approved test form to guide our testing. For instrumentation, we rely on IR testers, multimeters, clamp ammeters, tap position indicators, and approved phase loss simulation methods when necessary. The testing follows a clear, step-by-step script. First, we confirm the control supply, tap range, mechanical counter, selector settings, emergency stop, and limit switches. Next, we ensure the environment is safe with authorized communication before operating the OLTC. We then verify motor insulation and control wiring before operation. We operate the OLTC through the required tap range, checking local and remote tap indications while measuring motor starting and running currents for all phases. An approved phase loss check is performed only under authorized, safe conditions. Finally, we confirm the response of end limits, interlocks, alarms, motor protection, and operation counters. The OLTC must operate smoothly across the full range with accurate indications, proper limit actions, and normal current consumption, without abnormal alarms or mechanical binding. For documentation, the result package includes the OLTC test sheet, current readings, tap position tables, operation counters, alarm screenshots, and witness sign-offs. The hold point requires that a witness confirms the final tap position, selector status, and that no forced commands remain active. This ensures the OLTC is thoroughly tested and fully commissioned before returning to service. Here we have the schematic for power transformer frequency response analysis, which is a crucial part of testing and commissioning in the electrical grid. This diagram serves as a reference for the FRA measurement methods and winding connection configurations. Understanding this schematic helps ensure that transformers operate reliably and efficiently within the grid. It emphasizes how essential precise testing is before full commissioning. Today, we're going over the power transformer frequency response analysis test script, a crucial part of testing and commissioning electrical grids. The main goal here is to use baseline or diagnostic frequency response analysis to identify any winding displacement, core movement, or mechanical changes in the transformer. We start by gathering references like the manufacturer's FRA baseline, previous site records, vector group, tap position, and the approved FRA procedure to ensure accurate comparisons. The equipment needed includes a calibrated frequency response analyzer, shielded measurement leads, grounding accessories, specialized laptop software, and tools for exporting reports. The testing follows a step-by-step script beginning with confirming the transformer's tag, vector group, test method, tap position, oil status, and availability of a baseline. Then we verify that the transformer is completely de-energized, isolated, and safe for installing test leads. Next, we connect the source, reference, and measurement leads using approved methods to ensure valid readings. We perform the FRA sweep for each winding and phase in the proper sequence while maintaining consistent lead routing, grounding, and tap positions to preserve repeatability. After gathering data, we compare the traces against the factory baseline, previous site records, or sister phases to detect anomalies. Any trace deviations are recorded, along with possible mechanical interpretations and recommendations for engineering review. Finally, we remove all test leads, restore grounding and terminal covers, and archive raw FRA files and the final report. The acceptance criteria require that FRA traces be repeatable and align with baseline or engineering standards. Any significant unexplained deviations must be investigated before energization. The resulting package includes the FRA report, raw trace files, baseline comparisons, connection photos, tap position records, and witness sign-offs. Before closing, there is a hold point where engineering and commissioning witnesses review trace acceptance to ensure the transformer is ready for energization. This thorough process is essential for maintaining transformer reliability and safety.